any questions about homework or anything? Yep.
This question, exactly determinate.
Mm-hmm.
No, sorry, number 2.
Mm-hmm.
I was asking off, sorry.
Okay. Yep.
For stresses and beams, you said to do number 4 and 5, but we did that on the last assignment. Do we need to?
Oh, no, only do it once. I mean, you should do it more than once, but only turn it in once. That's what I mean. I mean, you can do it as many times as you want, but you have to do it once and turn that in. That's all.
What if we do 5 times and turn only 5 tries to?
I'll take it.
Do we get extra credit?
No, not point-wise.
Okay.
But there's a lot of kinds of extra credit, but no extra points. Okay, no questions? No homework questions? All right, the final is on Thursday. So remember that your final score, it counts as exam 5, and it also replaces one exam with a lower score. So if you have like one bad score or you missed an exam, the whatever score you get on the final replaces it, unless the final score is the lowest score of the semester, and then it only counts the one time. And it says on D2L that the last homework assignment is due tomorrow, but you can turn it in on Thursday. That's fine. I assume everyone's going to pretty much hang on to it. Any questions about the end of the semester?
Will the final just be problems, or will it be like?
Yeah, it'll be just like the other exams. It's just going to be a cumulative test up until now. It'll cover everything in the class. Any other questions? Okay. So the last topic in macroscopic deformations, the last type of macroscopic deformations and we can also use these in statically indeterminate systems, although it's kind of more of a pain in the butt than the other ones. Is beam deflection. And the idea of this is if you start with a straight beam and then you apply some loads, the beam does this, although obviously we're only dealing with small deformations, so we can't deal with beams that make changes like this. But if you measure the distance, and we'll call it the upward distance, from the original height of a point on the beam to the deformed height, we're going to call that lowercase v, and that's the beam deflection. Okay. Dang it. And this is all based on the theory of elastic beams. And the theory of elastic beams says that if you take the bending moment and divide it by the Young's modulus times the area moment of inertia, that's equal to the curvature of the beam at that location. This equation is true point to point, so this is true at a single location, true at every point. This term, E times I, is called the flexural rigidity. And you can see just mathematically what this says is for a given bending moment, if you increase the flexural rigidity, there's less of a curvature in the beam caused by a bending moment. If you decrease the flexural rigidity, there's more of a curvature in the beam, which just means if EI is high, the beam is stiff. It resists deformation. If it's small, the beam is really easy to deform. Curvature. Who remembers curvature in calc something? Something between 1 and 4. So curvature in a standard XY coordinate system is given by this formula. The Greek letter kappa, that's the curvature, is equal to the absolute value of f double prime of x divided by 1 plus f prime of x squared, and that whole denominator is to the 3/2 power. So this kappa is the curvature. And obviously this is a term we would prefer not to deal with. It doesn't take much looking at it to recognize that's a pretty complicated expression. But the good news is as long as f prime of x stays near 0, the curvature is about equal to the second derivative of the function. Okay, so that's as long as you don't have big changes in slope, as long as, in our case, our f is going to be that v, the deflection, and as long as you don't get big slopes that deviate a lot from the original straight beam, okay, we can approximate the curvature as the deflection double prime. So for us, and that means, because for us, we're always assuming small deformations, the bending moment divided by the flexural rigidity is equal to V double prime. M is a function of x. So finding the function v, finding the deflection v of x, this function that gives the deflection at every location, is a matter of solving this simple differential equation. This is as simple as a second order differential equation can be. So to solve that, you just have to integrate this twice. V prime is equal to the integral of m over ei dx. And v is equal to the integral of whatever that integral was. The thing to notice here is that each integral you take produces a constant of integration. And so when we integrate twice, we're going to have two constants of integration that we're going to have to deal with. And those are going to come from boundary conditions. So remember, each integral produces one unknown constant of integration. We'll solve for those using boundary conditions. Okay, so here are the boundary conditions that that we're going to use for beams. And there are, I guess I have it just divided up into two. The first has to do with joints. You can think of this as joints between the beam and the surroundings. There are two types that we're going to deal with. The first one is pins and rollers. And at any place that the beam passes over, passes through a pin joint or a roller, the deflection is equal to 0. That's a place where the beam can't move from its original position. So you can think of it as the beam is stuck at its original position. At its original height. To understand this, so if you have a beam that's originally like this, okay, I'll just draw it as a line. After the deformation, this beam can do all sorts of stuff. But at these two locations, where these joints are, the beam has to be at its original height. Okay, those joints prevent any other height from happening. the roller really doesn't prevent it from jumping up into the air, but in that case we wouldn't have equilibrium, and so we're going to treat it like those rollers keep that place on the beam confined to a single location. Any questions about that one? The other type of joint is a fixed joint. And at a fixed joint, you still, you also have that place on the beam confined to its original location. So V is equal to 0 at that point. But the slope of the beam is also locked in at that position. So V prime is also equal to 0. So to visualize that, if the blue is your original beam, due to the loads, the beam can do all sorts of stuff out here. But right at the wall, it has to have a deflection that's equal to 0, and it has to be horizontal. It has to be its original slope. Any questions about that, or like just trying to make sense out of intuitively why that is? Okay, and the last thing is, really you could think of this, so now this is the second type, that A and B were the first type, which are external joints. You could also think of any places on the beam as being fixed joints between one part of the beam and the adjacent part of the beam. And if you think about it that way, this makes sense, but at any points on the beam where the moment subfunction changes, the deflection at that line where the subfunction changes coming from the left is equal to the deflection at that line coming from the right. So in other words, the left and the right have to agree about the deflection. They don't have to be equal to 0, but they have to be the same. And the slope coming from the left has to be equal to the slope coming from the right. So let me draw a picture of this. Okay, so here's the original beam. And let's say here's the point where the subfunction changes. Then after the deformation, the subfunction representing the beam to the left of that point puts the beam into this shape. On the right, it puts the beam into this shape. But right at that point, the slopes have to agree and the heights have to agree. Okay, it's the same point. So you can't have any non-differentiability at that point. You can't have like a jagged peak. And you can't have differences in height, or else the beam is broken in two. So you can think of this as the two sides agree on the height and the slope. Any questions about that? All right, so let's do an example problem. We just want to calculate the total deflection at the right end of this beam. So let's say there's a cantilever at the left end. There's the beam. And we have a total distributed load, a uniform distributed load of 10,000 newtons per meter. The beam's 3 meters long. And let's say this is steel, so Young's modulus is 200 times 10 to the 9 pascals. And based on the cross section, the area moment of inertia is 8.3 repeating times 10 to the minus 7 meters to the fourth. And we want to know what's the deflection at the right end of the beam. Okay, first, what's the deflection at the left end of the beam?
0.
Very good. So if that was the question, you feel lucky. So the first thing we have to do is the internal loads calculation to figure out what the moment is as a function of x. And before we can do that, we have to calculate the external loads. So free body diagram of the whole thing. So there's a force vector r, there's a couple mr, and then now that we've chosen what to isolate, we can represent that distributed load as a point force. It's a total force of 30,000 newtons acting at the midpoint. So Newton's second law says Rx, Ry plus 0, negative 30,000 is equal to zeros. So this function, or this reaction load R is equal to 0, positive 30,000. And then the moment equation, I'll calculate that about the left end point where that force R is. So there is, we add in that couple, there's an MR. And then what's the moment arm of the 30,000 Newton force? Yeah, 1.5 meters. And is it positive or negative? Yep, that's a clockwise rotation, so negative. So the reaction MR is equal to positive 45,000 Newton meters. And now how many cuts do we have to make? So if you look at this picture that's up, it'll screw you up. You need to look back at the original picture. So there's the two endpoints. Are there any places between the two endpoints where that distributed load changes or point forces or anything? No, so we're just going to do one cut. Okay, so cut 1 represents all x values between 0 and 3. At the left end, we have an upward force of 30,000 and a positive couple of 45,000. The distributed load is 10,000, so when we treat that as a point force, this is just going to be 10,000 x. And it's going to be happening at a distance x over 2 from the end. And then we have the internal loads, T, V, and M. There's nothing going on about the x-axis, so I'm just leaving the torque out. So Newton's second law says 0, 30,000 plus T negative V. We almost forgot this. 0, negative 10,000 x. Is equal to zeros. So there's no internal tension. There's an internal shear force of negative 10,000 x plus 30,000. And now the moment equation about the left end point. We have the reaction moment, reaction couple of 45,000 Newton meters. Then there's a moment arm of x over 2 for this force of 10,000 x. And is that clockwise or counterclockwise? You want to, yeah, good. Yeah, exactly. Okay, so negative. I have to tell you this story. It's funny. Sophia, you should wake up for this. It'll be funny. Our dog just got a. You're on video now. Our dog, like we had this little fluffball dog that just got a haircut, and like he was just cut, like you couldn't see his eyes or anything. So and my son just got glasses. So last night our younger son was like, "How come everyone gets something new except me?" And I'm like, "What do you mean?" And he's like, "The dog got a haircut. You guys all have glasses." And I was like, "I don't know. What do you want?" He's like, "A mustache." He's 5 years old. Like, okay, good luck to you. Okay, so the moment equation, 45,000 minus this thing, plus m minus vx is equal to 0. And so m is equal to positive 5,000 x squared minus 45,000 plus Vx, so minus 10,000 x squared plus 30,000 x so negative 5,000 x squared plus 30,000 x minus 45,000. That's m. Okay. Is that what we were trying to do in this problem? Calculate internal loads? I don't remember. No. What are we trying to do? Yeah, we're trying to get the deflection. So we did all this to come up with the function for the bending moment, because then we're going to use that in calculating the deflection. So now the second derivative of the deflection is equal to 1 over EI times this function m that we just figured out. So that's 1 over EI, we can fill those in at the end, times this function negative 5,000 x squared. I left off this x. So negative 5,000 x squared plus 30,000x minus 45,000. And now we're going to integrate this to come up with the deflection function. So v prime is equal to, well, 1 over EI times mdx. And that is 1 over EI times 5,000 divided by 3, that's negative 1666.6 repeating x cubed plus 15,000x squared minus 45,000x. And then we have our first constant of integration, call it C1. And now to calculate the deflection, we integrate that. So the deflection is equal to the integral of v prime dx. Yep. I need what?
You said it, but you didn't write down.
Oh, I didn't write x. Thank you. And so now we get, integrate this, you get what's that going to be? 416. So, okay, negative 416.6 repeating x to the fourth plus 5,000 x to the third minus 22,500, bless you, x squared plus C1x, and now we have another constant of integration, C2. Okay, well, we almost have the answer. We have an expression for the deflection, but it still has two unknown constants in it. So we have to use what we know at the cantilever, at the wall, to come up with these constants. So now we're going to use the boundary conditions at the wall. To find C1 and C2. So the first one, let's use the fact that at x equals 0, because x equals 0 is where that wall is. V is equal to 0. So we have, going up to this expression for the deflection, we have that 0 is equal to 1 over EI times, all of these have x, have factors of x. So that's, 0 plus 0 plus 0. Then plus C1 times 0, so that's another 0, plus C2. So this tells us that C2 is equal to 0. And now we can update. Now we have a, slightly more information about what this deflection function looks like. Now what we have is that this deflection is a function of x is equal to 1 over EI times the quantity negative 416.6 repeating x to the fourth plus 5,000 x cubed minus 22,500 x squared. Yep. Plus C1x. And now there's no C2 anymore because we just calculated that that was 0. And now we'll use the fact that at x equals 0, v prime is equal to 0. Well, we have an expression for v prime up here. That was before we integrated to come up with the function for the deflection. So we have that 0 is equal to 1 over EI times the quantity. This will be 0 because x is 0. These two will be 0. And then plus C1. So we can use that to calculate that C1 is equal to 0. And our final function our final deflection function says v of x is equal to 1 over EI times negative 416.6 repeating x to the fourth plus 5,000 x cubed minus 22,500 x squared, and nothing else because we calculated that those two constants were equal to 0. Okay, is that what we were asked for? Almost. Actually, that's more than we were asked for. We just want to know the deflection at the right endpoint. This is the deflection everywhere. So now, so we want the deflection when x is equal to 3. So v of 3 is equal to 1 over 200 times 10 to the 9th times, this is also in the denominator, 8.3 repeating times 10 to the minus 7 times negative 416.6 repeating times 3 to the 4th power plus 5,000 times 3 cubed minus 22,500 times 3 squared. And you get a value that actually probably means this problem is pretty unrealistic. You get a deflection of negative 0.6075 meters. Okay, so the problem, those calculations were right. But the absolute value of the deflection is pretty big. And so that calls into, well, what's the problem with that value being so big? There are a couple possible problems. One is if the material is deforming a lot, there's a good chance that the stresses are really high. And so one possibility is that this thing would just break right off the wall. To figure that out, we just have to do a stress analysis and compare that to known limitations of the material. But specific to this calculation of deflection, what's a concern here if that value is that big? The whole curvature thing, right? This whole calculation. That's right. So this means the approach is questionable. Here. Because V prime does not stay close to 0, and therefore the curvature is not close to V double prime. Any questions about that? Okay, so now let's, well, I'll just write the problem, then we'll take a 10-minute break. The next example I'm going to do is a statically indeterminate system using deflection. Okay, let's say that we have a beam that is connected to the wall at the left with a fixed joint. And it also is connected to the ground by a roller at the right end. Let's say the length is 1 meter. And there's a uniform distributed load of 20,000 newtons per meter. And let's say we want to figure out what's the maximum deflection in this beam. And absolute value is what we care about. Everything's going to deflect negatively, downward. Okay, so first, in any statically indeterminate system, the first thing we're going to do is the statics. When we go through the statics equations, we're going to see that we don't have enough information to come up with the reactions. And intuitively, the reason that we're going to see we can't solve it using statics is because if you picture this beam being a rigid body, you could take away this roller and it still would be in equilibrium. And so if there are any redundant external loads, it's not statically determinate. So we're going to have to represent those external loads using variables and then go all the way through, calculate the deflection, and require that the deflection is equal to 0 at the right end, and that the deflection and the slope of the deflection are equal to 0 at the left end, and use that to calculate those external loads. Any questions about the flow of this problem? I think with these kind of problems, when you're looking back through your notes or right now, it's helpful to kind of skim them first and just remind yourself what the flow is, because the thought process isn't that hard for how to go through these. But if you just try to read from start to finish before kind of centering yourself on what you're trying to do, there's just so much calculations going on, it sort of obscures the big picture, So, okay, let's take a 10-minute break, and at 2:03 we'll do this problem.
To the statics.
Yes. Okay, steps. do the statics. We're going to see we need more equations. Then what? Internal loads. You guys should not expect Bob to answer every question.
It was a good study help.
Okay. Okay, then you should.
Then we'll see why I fail.
Internal. Do the internal loads. After the internal loads,
Then we find our, we use our formula.
then we find the deflection. So the deflection is equal to m over EI. And the boundary conditions. And then those give the extra that gives you the extra equations, and you can solve it for those external loads. And then we're trying to find the maximum deflection. So once we have a function for the deflection, we could just do it, look at, graph it, look at it, do it by inspection, or we could minimize the function, take the derivative with respect to x and set it equal to 0. Okay. So first the statics. At the wall, we have a force of R and a couple MR. We have a total force of 20,000 newtons. And then we have the roller at the right end. I guess I'll call this one RA at the left and RB at the right. Newton's second law says RAX, RAY plus 0, negative 20,000, plus 0 RB is equal to zeros. And the moment equation says MR, I'm doing it about the left end point again. So MR minus a moment arm of 0.5 times 20,000, so that's 10,000. Plus a moment arm of 1 times RB is equal to 0. So RAX is equal to 0. Let's not count that in our list of equations. We'll just set that aside. So our two useful equations are RAY plus RB is equal to 20,000. And the second equation says MR plus RB is equal to 10,000. That's two equations and 3 variables. So we need more equations. This is statically indeterminate. How many cuts do we have to make for the internal loads? Okay, why are we even doing internal loads? It doesn't ask for internal loads. Yeah, we need a function for the moment so that we can calculate the deflection. So how many cuts? Well, I'm trying to throw you off showing you this picture. One cut, yep. So the first cut is valid for all x's between 0 and 1. I call this cut Texas because it's all where all the x's live. I just made that up.
George Strait.
I'm going to use that again in the future. Okay, so what do we have? R-A-Y. We don't know what that is, so we'll just leave it like that. And a moment here, MR. And then our distributed load is 20,000, so the point force is 20,000 X. And then we have T, V, and M. So Newton's second law says 0 R-A-Y plus 0 negative 20,000 X plus T negative V is equal to zeros. So T is 0. We don't care about that. We do need this V, though. So V is equal to R-A-Y minus 20,000 X. And then the moment equation. We have MR. The 20,000 X has a moment arm of X over 2, so that's, and it's negative, so that's negative 10,000 X squared. Plus M minus Vx is equal to 0. So the bending moment is equal to negative MR plus 10,000 X squared minus 20,000 X squared plus R-A-Y-X. And you can simplify that to, I guess I'll write that, R-A-Y-X minus MR minus 10,000 X squared. Okay, so now we have our function that represents the bending moment. And the deflection is equal to, oh, I didn't give any, did I give values for this, the material values?
No, sir.
Let's pretend I did. And let's pretend that the ones I gave you were Young's modulus for steel. And an area moment of inertia of 1.0 times 10 to the minus 7 meters to the fourth. Okay, so the second derivative of the deflection is equal to 1 over EI times R-A-Y-X minus MR minus 10,000 X squared and so if we integrate that, we get that V prime is equal to 1 over EI times the quantity ray over 2 times x squared minus mrx minus 3,333.3 repeating x to the third. And then don't forget the constant of integration, so plus C1. And now the integral of this with respect to x is the integral of this with respect to x. So the deflection is equal to 1 over EI times the quantity RAY over 6 times x cubed minus MR over 2 x squared minus 833.3 repeating x to the fourth and then outside the parentheses plus C1x plus C2. All right, so now what do we do? Yeah, now the boundary conditions. And we have 3 boundary conditions. At x equals 0, the deflection is equal to 0. At x equals 0, the derivative of the deflection is equal to 0. And at x equals 1, the deflection is equal to 0. Okay, so boundary condition 1. Plug in 0 for all the x's. So v of 0 is equal to 1 over EI times all of this is 0 plus 0 plus C2, and that has to be equal to 0, so C2 is equal to 0. And now we can update. So the deflection function is equal to 1 over EI times the quantity RAY over 6 x cubed minus MR over 2 x squared minus 833.3 repeating x to the fourth, close parentheses, plus C1x. So now we can use the second boundary condition that says plug in x to the v prime expression and you get a v prime that's equal to 0. Let's see, this thing gave us, okay, so I put it all in the integral stuff, but this expression says v prime is equal to 1 over EI times all this stuff in parentheses plus C1. So if we plug in x equals 0, we get that v prime at x equals 0 is just equal to C1. So v prime at 0 is equal to c1, and that has to be equal to 0. So we can update this function again, and we get that the deflection is equal to 1 over EI times the quantity RAY over 6 x cubed minus MR over 2 x squared minus 833.3 repeating x to the 4th. And we don't have any of those constants left. The first two examples I did here, all those constants of integration go away. That doesn't have to be the case. That just has to do with where those joints are. Okay, so we have this expression. Now what do we do? Are we any? I mean, we're closer, but this still, we don't have numbers for this, and we want to have numbers for these variables. So now what? Yeah, we still have one more boundary condition, and that's going to let us solve for one of these two variables, or at least come up with another equation. So boundary condition 3 says when x is equal to 1, v is equal to 0. So the deflection at 1 meter is equal to 1 over EI times the quantity RAY over 6 minus MR over 2 minus 833.3 repeating. And that has to be equal to 0. Well, this isn't an equation we can solve for anything, but we can use this as to go into our system of equations. These are our original two equations. So let's call this equation 3. Multiply both sides by EI, and you get RAY over 6 minus MR over 2 is equal to 833.3 repeating. What do we have now? We have two equations and three variables there. We took care of the constants of integration without adding to the system. So now we still have we still just have three variables, and so we should be able to solve this system now. All right, well, let's write it out as a table. So our variables, we have a system of 3 and 3. Our first variable is RAY. Our second variable is RB. And our third is MR. And these are our equations. The first equation says RAY plus RB equals 20,000. So RAY, we have one of those. RB, we have one of those, and the constant is 20,000. The second equation, where is this thing? I went too far. MR plus RB equals 10,000. So 1 MR, 1 RB equals 10,000. And then our third one says RAY's 1/6, MR's -1/2, and a constant of 833.3 repeating. I think you get an RAY that's equal to 12,500, an MR that's equal to 2,500, and an RB that's equal to 7,500. So now we can give the final function for the deflection. The deflection is equal to 1 over E is 200 times 10 to the 9th. I is 1.0 times 10 to the -7. RAY over 6. RAY over 6. So what's that? 12,500 divided by 6 is 2,083. Is that right? 283.3 repeating, and that was times x cubed. And then MR over 2 times x squared. That's 1250 x squared. Minus 833.3 x to the 4th. And that's it. All right, so we can simplify this a little bit. So this is 1 over, well, can someone just divide these terms out for me? 200 times 10 to the 9 times 1 to the -7 is 2 to the 4th. So 833.3 repeating divided by 20,000.
$0.41665.
0.416. Okay. X to the 4th. And then, or is that the,
That's it. With that,
okay.
1250 divided by 0.625 squared.
Okay.
1.04165.
1.0.
4165.
Did you do divided by?
Okay, so x cubed, 1.04165 x cubed.
Are these all off by a factor of 10?
I hope
'Cause-
not.
Okay, that's what it looks like to me.
If you back into -6, or kind of -6.
Okay, so this is 0.04. This is point
What?
0. Point,
No,
is that
sir.
no?
0.04. Yeah, 0.04167.
0.04167. And then this one divided by 20,000 is
0.0625. Yeah. And then the other one is 1.04.
oh, that's this one. Okay.
Yes, sir.
So this is the fourth.
Well, that is
0.1064. This is the x squared.
Yep.
This is the x third.
Yep.
Okay.
Something like that.
Okay. So,
That's not what I got.
oh!
The last two numbers.
Okay. I'll keep writing until you guys get tired of typing in numbers in your calculator. The FBI could be watching my video channel. I don't want to go to Guantanamo Bay for this. 0.104? And what's that? Okay. And then
I got 0.0625
6 squared.
Will the x cubed be a positive number?
Yes. And now we all agree? Okay. All right, so that's the deflection. So where is the deflection maximum? Well, we've already seen some sort of interesting stuff going on here. If you had to guess what was going to happen, why is there a whole blank page there? Okay, look back at the original problem. If you had to guess what was going to happen here, you might guess that the wall wouldn't produce any moment, and you would have equal forces at these 2 points. But that's not what happened. We did have a couple at the wall, and there was a difference in the vertical reaction forces produced at the 2 joints. That's sort of interesting. And so you might also think that the maximum deflection is going to be at the middle. That would be the most boring answer. But I suspect that that's not going to be the case. I don't know because I didn't go all the way to what I asked for last year when I did this. So this is already a better class than it was last year. Okay, so how do we find the minimum value of the deflection?
Put in 0 for x.
Yeah, take the derivative and put in
Or
0.
derivative.
Yep, right. So, so we want to minimize v of x. So we're going to set dv dx equal to 0. That is, what's 4 times 0.04167? Oh, that's going to be 166. I know what that is. 0.16 repeating x to the third, right? And then what's 3 times 0.104? That's 0.312 x squared. And then 2 times that is 0.125 x. And set that equal to 0. So you can factor out an x, and you get, so 0 is equal to x times negative 0.16 repeating x squared plus 0.312 minus 0.125. What is it?
Got an X on the 0.312.
Thanks. And so you can use the quadratic formula for this stuff on the inside. So what do you get? Tell me if you get the same thing. The minimum, I believe, is negative 0.667 meters. Yeah? No?
Can't go backwards,
Yes.
can we?
No. Oh, for deflection? That just means it's below the original height. So that's what we'd expect.
Okay.
And then, you'll get two other roots here. Okay, first things first. This number is too big to be realistic. But this is a cubic equation. You're going to get 3 roots. What do the 3 roots mean? Well, this is the 2 roots of the quadratic factor are just going to be 2 candidates for maxes or mins. They're going to be critical points. And then the third root is x equals 0. So what's going on at x equals 0? Why is that in there? Well, I mean, it's also a critical point, but in this case, it makes sense that that has to be a root of this deflection equation, because at x equals 0, it's a fixed joint, and we required, one of our boundary conditions was that the slope of the deflection is equal to 0 at that fixed joint. So anywhere where you have fixed joints, you're going to have critical points for the deflection. Anyone have any questions? Yep.
So why did we minimize the function when we were looking for the maximum?
We're looking for the maximum absolute value of the deflection. This whole thing, all the forces are downward, so we're not going to get any deflections up. Everything's going to. So we could plot that function out and look at carefully what it's doing, but it's going to do something like this. Oh, x is, oh, I told you that wrong. That's the x value. That's one of the x values. Oh, we don't, that's not what we want. Yeah, is there, right, it can't go backwards. You're totally right. Sorry about that.
It's okay.
Okay, so what's the positive x value?
I got 2 positive X values.
Oh, you did?
I have 0.58 and 1.29.
What that says is if you plotted that function at those 3 places, it gives 0. So you find
That's right. Those are just the x values, and then you plug those values into the deflection to get the, yeah. I'll edit that out of the video, don't worry. But I'm still going to leave in that joke about Texas, because that's gold. Okay, so 0.58.
0.58 and
1.29 we don't care about, because that's past the end of the beam. So that's where the minimum is, and the value of this deflection is, I got a value for the deflection of negative 0.0054 meters. Is that what you got plugging those in?
Yeah.
Okay. And that's totally believable. That's 5 millimeters of deflection. So this distance is 0.58 meters. So that minimum did happen to the right of the center line. And the amount of deflection was 0.0054 meters. Any other questions about that one? Okay, well, let's stop for today, but tomorrow we'll do an example where we put all this together. So let's say we have a bar. It's 2 meters long. And at the midpoint, we have a torque and a downward force. So let's say we have a downward force of 5,000 newtons. And a torque of 2,000 newton meters. And the temperature increases 60 degrees Celsius. And let's say we want to find a stress tensor at that dotted line. Yeah. And we'll have to choose a place on the cross section. So let's say along the neutral axis. Okay. All right, that's all.